Welcome to Chapter 16, Acids and Bases. Make sure that you've got a pencil, a place to write down some notes, and a periodic table handy. And let's outline how the videos and how Chapter 16 is going to go here on the left-hand side. The first two sections of Chapter 16 define what acids and bases are and allow you to identify them in several different ways. And then in sections 3 and 4, we learn about pH and other P scales like pOH and how they're related to the hydronium or hydrogen ion and hydroxide ion in a solution, and a calculation piece called the pH square. In section 16.5, we look at strong acids and bases and calculations associated with them. And in the last three sections, we look at weak acids and bases and how the equilibrium constant, called K for acid and K for base, are related and tell us a lot about mathematically how these weak acids and bases act. First, just a little bit of chemistry in your everyday life. You learned probably in biology class that the building blocks of proteins are called amino acids. And in past video casts, you learned that an amine group is one that contains nitrogen and two hydrogens and then an unshared pair of electrons, and is allowed to easily gain a hydrogen. And you also learned about carboxylic acid groups and that they have a C double bond OH, which allows them to release a hydrogen and therefore be an acid. And so amino acids are both. They're both an acid and a base at the same time. And this is the backbone structure of an amino acid, and what separates the amino acids from one another is this side group right here. I'll call it an R group. This group right here separates each amino acids from one another, and all of them have this amine group on one end and this carboxylic acid group on the other end. Here are two examples. This one, called glycine, has the amine group right here with an N and two H's. And then in the middle structure, this branch chain right here is just a hydrogen for glycine, and then a C double bond OH. And this is alanine, and this one has a CH3 group off of this branch chain right here, and that's what separates it or makes it different than glycine. But you can see it still has the amine group and then the acid group over here. And these are symbolized by some letters, sometimes just by a single letter, and then those of course go together in a pattern, and those are what make up protein. These are the types of things we're going to learn about and be able to identify throughout Chapter 16. First, let's go way back. Let's go back to the early 1800s. The early 1800s was the first time that somebody defined acids and bases, and his name was a chemist named Savante Arrhenius. And Arrhenius defined an acid as something that increased the hydrogen ion concentration in solution, and he defined a base as something that increased the hydroxide ion concentration in solution. These actually would do both at the same time. Hydrogen ions would come from here, and then these would take an H away from a water and therefore increase the hydroxide ion concentration. This explained why hydrochloric acid acted acidic, because when hydrogen chloride gas was dissolved in water, it would increase the H plus ion concentration, and therefore it was defined as an acid. About 100 years later, along came two chemists at the same time that weren't necessarily working together, but came up with a more general definition. And their names were Bronsted Lowry. And so for the rest of the chapter, we'll usually talk about the Bronsted Lowry definition of an acid and a base. And they said that acids were donors of hydrogen ions. But before we get to that definition, it's chemistry, so it's got about 6 different ways of naming this species right here. An H with a little plus dissolved in water is known as a hydrogen ion. An H+, it is also known as a proton, because remember, hydrogen has one proton and one electron, and if you remove that electron, making it positive, the only thing left is a proton. And so this is many times called a proton. And this hydrogen ion, or this H+, reacts with water molecules, and it forms this H3O+ ion. And so H+ and H3O+ are interchangeably used. And H3O+ has the fancy name hydronium ion. And so sometimes H+ is called the hydronium ion. H+ and H3O+ are interchangeably used. Another fancy way of saying hydrogen ion is a hydrated proton. Hydrated meaning that it's dissolved in water and it has a little plus next to it. So they defined an acid as something that donates or gives away these H+, these protons, these hydronium ions, these hydrated protons. So here's an equation to illustrate this. Here's HCl, just like Savante Arrhenius looked at, and here's water, and then it forms the chloride ion, and then the H is donated to the water right here, and it forms H3O+, and so the proton donor is the hydrogen chloride, and the proton acceptor is the water, and so this is our acid, and this is our base. Now we could also look at this equation backwards, or in the other direction, from right to left. And when we do this, we could also define an acid and a base. And if you look at it backwards, from right to left, you see that chlorine is the thing that gains a proton. And so we call that the proton acceptor, or we call that the base, but we give it a fancy name because it's backwards, and we call it a conjugate base. So chloride ion is the conjugate base of HCl. H3O+, or the hydronium ion, is the proton donor, and since it gives away a proton, we call it an acid, but since we're looking at it backwards, we call it the conjugate acid, or the thing that gives up a proton in the backwards direction. Being able to identify the donor, acid, acceptor, base, backwards donor, conjugate acid, and backwards acceptor, conjugate base, are critical to the understanding of this and all future chapters. So Bronsted Lowry defined acids as proton donors and bases as proton acceptors. And so to help you remember it, you can remember a base is a big giant bee monster. He's got big scary teeth, and he's the one that eats hydrogen ions, or he's a proton getter. And he's got little arms and little legs to run around getting hydrogen ions from different places, the bee monster. And so once you understand that acids are proton donors and bases are proton acceptors, you now can identify what are called conjugate acid-base pairs. And in a conjugate acid-base pair, we have something that can give up a hydrogen, and then what's left over after that species has donated or given away its hydrogen. And so these are called a conjugate base acid pair. And the only difference is the H+ right here. These are called a conjugate pair. More general, you can say that the acid is going to have one more H than the base. And these are called a conjugate acid-base pair of one another. And so now, let's take a look and let's just do a little bit of practice in identifying and writing what is the conjugate base of. And let's do a bunch of these as examples. So HClO4, what would be its conjugate base? Well, remove the proton, and ClO4- would be remaining. This would be the conjugate base. What would be the conjugate base of H2S? Well, remove a proton, and the thing remaining would be H and S, and it would have a -1 charge because it lost a hydrogen. what would be the conjugate base of pH4 positive? Well, remove one hydrogen and you'd have pH3, and it wouldn't have a charge now because it would go down in charge one space. And what would be the conjugate base of HCO3 minus? Well, remove the hydrogen and you'd have CO3 minus 2. It would go down one charge. Okay, let's go the opposite. What is the conjugate acid of? So now these would be bases that would be accepting a hydrogen, and it would be what would exist after it gains a hydrogen. So Cn minus, gain a hydrogen, it would be HCN. SO4 2 minus, gain a hydrogen, it would be HSO4, and then what would happen to the charge? It would go down one because, it would go up one because it gained a positive hydrogen, so it would be minus 1 now. HOH, gain a hydrogen, H3O plus. So this would form the hydronium ion. That would be the conjugate acid of water. Last one, conjugate acid, gain a hydrogen, H2CO3. It would go up in charge one space. Good luck with your conjugate acids and bases.